Okay, thanks, Odile, for the introduction. In fact, it was slightly longer than my seminar today. So, and you reminded me of a lot of things that I've done. Today I will actually be talking about something that is, well, part of my interest. And it is, I think, particularly interesting for the audience here because it deals with practical issues as well as, of course, the theoretical considerations. And it is a very, I have to confess, it is a fairly long introduction to the topic, but I assume that the majority of the listeners are not familiar necessarily with the topic. So I have to introduce it nearly from scratch, not totally from scratch, but nearly from scratch. So essentially, we are dealing with earthquakes, and in particular, we are the topic here is understanding how, to what extent, the local environment is actually affecting the impact that earthquakes have on essentially on buildings. The theme here is very simple, but essentially represents what is generally happening. You have a source, which is a fault, not necessarily very deep. In fact, most destructive earthquakes are in the first 10 kilometers of depth, and the destruction takes place very close to the location of the hypocenter. And in the study of the seismic risk overall, a first step is the seismic hazard. The seismic hazard is an effect of the presence of seismic sources, the type of propagation of seismic waves, and site effects. Site effects means that the local conditions, for instance, weak sediments or topography, may amplify the effects locally, and the amplification is sometimes very, very intense. My focus here will be particularly on the shallow surface. Shallow means the first tens of meters. And I will introduce you to what is a general approach, or at least one of the approaches that is taken to assess the risk for buildings due also to site effects. I will not get into the details of the buildings themselves, how they react, because this will also be part of what the next speaker will talk about. So we'll concentrate essentially on the amplification effects near the surface. Okay, this is still part of the hazard, as we'll see, because the hazard is the composition of the location of sources, the propagation, and the site effects. Okay, I'm sure that you have some background in waves, well, that's for sure, and for sure also in elastic waves. But let me make it clear that we have two body waves, P waves and S waves. You will get the slides here, so I don't want to get into the details of all the derivations and so on. But essentially, these are two modes of propagation of the distortion and deformation due to a seismic source. The speed of the shear waves is substantially lower than the speed of the P waves, and for this reason, in seismic exploration, P waves are preferred. Exploration, I mean active sources that are used to investigate the subsurface. On the contrary, in our topic today, the main actor will be the shear wave. And I will try to convince you that this is the case and why. If you look at the typical seismogram from an earthquake, you will see the first arrival are the P waves, the second arrival are the S waves. P stands for prima and S stands for secunda from the Latin. Therefore, these are first waves and second waves. Okay? For this seismogram, you cannot really tell much. You can only see the difference in arrival time. Okay? There is one further type of waves that is actually pretty common in our experience every day. These are called surface waves. Surface waves are similar to the waves that you see in a body of water, for instance. And they are due to the same reason. Essentially, as the air above is very soft, it does not react in any way to the deformation of the soil. The soil must, by the soil and the water, the system below must self-balance the stresses. And in the case of solid materials, you will get a deformation of the surface that is bounded by air, and the compressive and shear stresses must balance each other. The effect is to produce surface. They are particularly intense because they spread only on the surface, because their source at the surface tends to produce a lot of energy in terms of surface waves, but their depth of penetration is small. This is a typical graph that is showing the amplitude as a function of depth normalized on the wavelength. We are about at one wavelength depth, okay, in terms of surface waves. And the speed of surface waves, in particular these ones that are the classical Rayleigh waves, is very similar to the speed of shear waves. Therefore, we'll find these waves at the end of the lecture today, because they are very informative in terms of the propagation characteristics of shear waves. Okay, but they are not the most dangerous waves in terms of earthquakes. The reason why is that the earthquakes do not come from the surface; they come from depth, and the damage is essentially in the region on top of the hypocenter. Okay, the damage can be substantial. The Amatrice earthquake less than 10 years ago, and this is before and after the entire small city was destroyed. Okay, but keep in mind this scheme, okay, where the destruction is actually very close to the hypocenter. Therefore, surface waves, yeah, they take place, but they take place in terms of very low frequency, not very energetic, and they propagate very far. But they're interesting from the seismological point of view, but they don't cause the major destruction. In fact, if you look at the geometry, the hypocenter is below your feet and the energy comes vertically up. When you get the wave, the P wave is in the direction of in the vertical direction, essentially. So it is soliciting the building in a direction for which the building is actually constructed. So the building will not suffer in general much from P waves. Of course, it depends on the energy, okay? But the disaster is caused mostly by shear waves, because the shear waves comes to the surface also nearly vertical, the shaking is nearly horizontal, and this means that you are shaking a system that is not built to resist horizontal stresses and horizontal displacements. So the upper floors tend to stay still while the basement is moved suddenly on the side, okay? Unless there is some bracing that I summarize in this kind of very simple scheme that is actually keeping the system more rigid in the horizontal direction, most of the damage will come from shear waves. If you look at the hazard, overall hazard maps that is generally found in the literature, just be aware that they are produced in this way. First of all, this is the expected peak ground acceleration in the horizontal direction, because we are interested in S waves coming from below. And this is actually computed in a stochastic manner, probabilistic manner, in the sense that it is the expected acceleration in 50 that has a 10% probability of exceedance in 50 years. Okay, which does not mean it is the largest possible acceleration, and also it is computed on solid rock, so it is not taking into account shallow amplifications. Okay, it is on solid material. And you can see maps like this for Europe, and of course also for Italy. This is the base for the first computation of hazard. Okay, so the first thing is the hazard in terms of expected accelerations. Be aware that if you want to transform that into risk, but we will not talk about this, in fact, but if you want to convert this hazard into an actual risk, you would like to take into account the vulnerability of the buildings, as well as the density of population or of productive activities and so on. Okay, so this is a classical definition that is given in terms of seismic risk overall. But we will go back to the hazard only, and I will concentrate on the shallow effect. The shallow effects are important, and here you have an example also from a recent, well, relatively recent earthquake in central Italy, where the earthquakes are not particularly strong, but the building quality is not particularly good, and the system is very heterogeneous. Here you see this is a village of Chesi, and it has two fractions. One is a lower fraction, one is a higher fraction, and the distance is only 350 meters. Okay, and the density and the intensity, this is a Mercalli intensity scale of the damage was totally different below with respect to above. Okay, this is a scheme. So the upper part of the village, okay, was on solid rock. The lower part of the village is in a valley, okay, sedimentary valley that amplified the response. Essentially, you can have two types of amplification. The first is the one I just talked about, and it is the one we will concentrate on because it is the most common. The local amplification due to the presence of weak soil layers. It is essentially like saying I'm having like two springs, okay? The spring, a very solid spring below and a weak spring above. If I start shaking the spring below, the shaking, okay, essentially the spring will not elongate much, and it will exchange the force with a weak spring. It will have to elongate much more in order to balance the forces. So the effect is to amplify the displacement, and the displacement is the basis for destruction. Of course, we are talking about shear displacement, but the parallel with the spring is appropriate. Therefore, this kind of amplification can take place in 1D because of stratification, or in more complex 2D or 3D setup because in valleys or in other landforms, you may have also focusing and defocusing. But essentially, it is an effect of amplification due to weakness of the soil layers. You can also have topographic amplification because when you have a hill and the energy comes from below, since the elastic energy cannot radiate into air, it tends to focus on the top. Okay? There are also pretty clear effects of this kind in hilly environments. So the scheme, and now I need to go fast a little bit, but the scheme involves a couple of different concepts. Okay, one is the spring concept, if you like. Okay, so you have a seismic source. This radiates energy, of course, in all directions. If you have a seismometric station on solid rock, it will record this kind of seismogram. If you are in a valley, as you move towards the center of the valley, and if the valley sediments are weak, the shear that is coming to the surface, the shear movement will be amplified. And therefore, here you have a seismogram that is much, much more powerful than the one you have on solid rock, which is very similar to the one you have at the base of the sedimentary sequence, particularly if you have like a few tens of meters. This is one effect. There is also another effect. If you have waves coming from below, they get through the sediments, they get reflected from the surface because of the very strong impedance contrast. They get reflected back, and then they encounter the new waves that are coming up because generally the coda is very long. We're talking about tens of seconds, if not minutes, and therefore you will tend to excite the resonation frequencies of the soil layer itself. You can have peaks of resonance that are on top and above the amplification due to the weakness itself. Okay, so you have to consider an amplification due to the weakness in terms of maximum displacement for one shot, so to speak. But considering that these waves come wave after wave, you also have resonance phenomena. If these peaks of resonance are similar to the peaks of resonance of the buildings, you have a serious problem. Okay, we're always talking about shear stresses, so horizontal displacements. As for the topographic amplification, The idea is very simple. I will not get much into this. Essentially, you have a plane wave coming up, and of course, the energy density will have to increase because the energy conservation will, by and large, be satisfied. But at the very top of the hill, you might have larger displacement and accelerations, of course, than you have at the bottom of the hill. Now, let's introduce briefly what is the general framework also in terms of legislation. And in Europe, we all refer to Eurocode 8, of course, through different national implementations. But essentially, the idea, well, it is a bit complex at times. Eurocode 8 is a construction code, okay, for all constructions, for all buildings. But it has also an anti-seismic part. And the idea is you have to start from the maps of hazard in terms of maximum acceleration you get at any particular place in the territory. Okay, actually, these accelerations, here you have the exact description of how this is computed, of course, based on assumptions and what we know, can actually be computed at a very small scale, so to speak, at a 10-kilometer grid. Here you have the Veneto region, this is the Abruzzo region, central Italy, you see the dots. Okay, so this is a starting point to calculate the acceleration that will be placed on the structure. But in order to have the actual acceleration at the base of a building, you need to take into account the amplification effects. And to make a relatively long story relatively short, this is a classical table from the Eurocode 8 that classifies the ground type as A, B, C, D, E, and then spatial types S1 and S2. And the first 5 go from the best soil A to the worst soil E, according to essentially one parameter, which is the called VS30. VS is the velocity of shear waves, and 30 means it is the average of the top, if you like, the shallowest 30 meters. Why 30 meters? Well, because this is copied from the United States, where in California they use 100 feet. Okay, so it's about 30 meters. It is just an acceptable thickness. And if the velocity of shear waves on average is above 800 meters per second, this is solid rock. Okay, we don't need to take into account any amplification. If the velocity decreases all the way down, maybe to below 180 meters per second, then there will be some provisions to compute amplification, and we'll see what kind of provisions. The characterization of the soil can also be done not only by measuring VS, but also using standard penetration tests, which is a typical geotechnical thing you can do, or cone penetrometer tests. But these are weaker ways of measuring the essentially there is some correlation with the VS, but it's not very solid. Okay, so it is by far preferred to use the VS30 as a parameter to classify the ground type. This is a definition of the VS30, and I will just briefly make a distinction here. Okay, I will be talking only about the so-called standard approach or the simplified approach, which simply means that if you have a ground type A, then the amplification is null because the factor is 1. In B, C, and E, you have a 1.25. In the D case, you have 1.35. Okay, that will also be modulated according to the frequency of the building, but this is the amplification that will be applied to the expected acceleration at the base of the building. And then from then on, you will transfer that to the building response. This is a very simplified approach. For spatial categories, for large buildings, for important buildings, and so on, you have to run a local seismic response analysis, which is much more complex than this because it has to take into account also the non-linearity of the soil response and sometimes the plastic and attenuation behavior of the soil response. But I will just stick to that. The purpose of this introduction is to make clear to you that the velocity of shear waves is crucial. It's crucial here, it's crucial also in the spatial studies. It is the way the characterization is actually conducted. And let me just jump this. These are the spectra, so-called response spectra, that are used to calculate the response on the buildings. So if you have a building that has a period of 1 Hertz, so the period one second, sorry, so frequency 1 Hertz, the amplification is not going to matter too much for A, it will be more for B, C, and D, more for D, but it would be worse if you have a building that has a natural period of 0.25 seconds, where the amplification is much bigger for all ground types. Okay, so this is a simplified. In fact, what you have to do is to calculate the response you expect given some types of expected accelegrams that you expect in that region, and blah blah blah. So, but this is the local response analysis that I don't really want to get into. Okay. From my point of view, now it is clear that we need to characterize the subsoil in terms of shear wave velocity. So the rest of the presentation will be dedicated to that only. And I will try and get into the discussion by classifying different methods, okay? Of course, you have methods that are based on boreholes. So therefore, I will call them invasive, not totally invasive, but still invasive. And methods that are based on surface measurements only, okay? And among these ones, I want to draw your attention particularly to the surface wave method, because they provide a lot of useful information. One reason why the characterization using on-site geophysical techniques is difficult is that you need to compute the shear wave velocity, but the shear waves are not the ones that arrive first. Therefore, you will have the interference with P waves. Also, and this is another important point, if you have any kind of elastic wave that is impinging on an interface with an angle that is non-zero, that is on 90 degrees, if you like, it's not perpendicular, the wave will generate two types of reflected waves and two types of refracted waves. So a P wave, a P reflected wave, but also a shear reflected wave, and the shear transmitted wave and the compressional transmitted wave. Essentially, this is because the angles must be, they are such because of Snell's law that the balance of stresses locally cannot take place unless you take into account also the other shear, the other type of wave, the other type of deformation. This is in essence means that if I produce a shear wave, in general, at first interface, I will also get some P wave in return. This is a problem because it will be difficult to identify shear waves alone unless I operate in a different way. And the different way is the so-called SH approach. So you essentially, if this is the plane that you have in front of you, you hit perpendicular to this plane. So the shear is actually perpendicular to this plane. The wave propagates down, hits the interface, and given the type of deformation with respect to the geometry of the interface, you will not produce any P wave. So SH travels alone. Okay? Therefore, that's one of the possibilities, using SH waves. We will use them most of the downhole applications and in most of the surface applications, as you see. An exception is the surface waves, because surface waves depend so much on the velocity of shear waves that by analyzing surface waves, you have information about shear wave velocity directly. Okay. Now, so essentially, this is the truth of different technologies you can use. We can use cross-hole measurements, downhole measurements, or uphole, if you like to put the source down. We have well logs where you have source and receiver in the same wells. If you don't want to drill wells, well, having some downhole, for instance, is always useful, but downhole is only giving you information very local, and it is expensive. I mean, a downhole has to reach at least a 30 meters depth, and the entire system must be cemented, as we'll see. So it is an expensive borehole. It can easily be 20, 30,000 euros each. Therefore, you cannot afford many downholes. What from the surface, well, you can move wherever you want, okay? So you might have more uncertainties, but the mix between non-invasive methods and downhole, or in general cross-hole methods, is actually a good match in terms of money balance. Well, the most sophisticated approach is a cross-hole, because you have two boreholes that are facing each other. The distance cannot be too large. We are range is maybe 2 meters, okay? 2 meters distance over 30 meters depth. You lower source and receiver at the same time, or if you want to do also, you can do tomography, but the minimum is the two at the same depth. You generate S waves. Now, S waves are easy to generate in the vertical direction, and you have to hope that there is no interface below that is actually interfering, producing P waves. But you may be lucky, okay? In order to remember that because of the Poisson effect, every time you hit transversely, you make also the system expand. So you also generate a P wave. For this reason, we will have to do something to try and cancel the P wave, okay? But the geometry is fairly simple, okay? We call the arrival time on the other side, you know the distance, you suppose you know the distance, you divide distance by time and you get the velocity at any depth. There are some issues, and maybe I already talked about some of these issues. First of all, the casing must be properly cemented to the outer wall, because you have to have a system that is not vibrating by itself. It must be in touch with the formation. Also, I failed to say that, but these sources and receivers must be clamped to the walls, and the walls generally are the casing walls, unless it is an open rock, okay, that can stand alone. But we are interested in most cases in soft soils, so they have to be cased. And between the casing and the drill hole, you must have some cement. Okay, that's why everything is also expensive to make. You have to be careful also in terms of the position of the boreholes, because you assume that you are parallel, but sometimes they are not. Okay, you have to be careful in many respects, but the approach is relatively simple. So you have to generate the S waves and identify them essentially in the recordings. You can also generate SH waves by using the torsional source, but this is less commonly used, at least in boreholes. Okay. So the idea is, I take my source, I hit it from the bottom first, I hit from the top again, essentially with two sliding hammers. What I obtain are two seismograms on the other side, similar to these ones, where the P waves are essentially the same, because it doesn't matter if you hit down or up, it expands, everything expands. But it is different in terms of the S wave. So the polarity of the S waves is opposite. So if you take the subtraction of these two traces, you tend to remove the P wave and you amplify the SH wave, the SV waves. And then everything is simple in principle. So of course, you have advantages. You may have some problems in the conversion of SV to P because you don't use SH really. And the main disadvantage is that it's very costly. Therefore, the most widely used approach is the downhole acquisition using SH waves. So essentially, you have a geophone down there that is sensitive in 3 directions, 3 components, and you will search for the arrivals on the horizontal components, because you're going to hit the surface horizontally. You're going to have something there, you're going to hit horizontally by friction. This will produce a shear wave that is going down. But again, you will also produce P waves. So if you have anything on the surface, you have to hit it from both sides in order to do the same subtraction and amplify S waves with respect to P waves. The acquisition is relatively simple as the one that I described. And here you have an example. This is the same geometry, where you have the P wave arrivals as a function of depth and the S wave arrivals as a function of depth. Okay, of course, you are interested in this guy here, and here you just mark the phantom of the P waves that are still present after this subtraction. So the identification is relatively simple. What next? Well, essentially, it is a downhole. It is a progressive increase in arrival time that is due to the geometry, right? So as you go down, you will get more and more delay because of the simple geometry, not because of the velocity. So essentially, if you want to identify the velocity, you have to identify the first arrivals and then identify the slope of the time versus depth line. Okay, this is a bit tricky. I mean, in this case, it is really simple, simply explained. But sometimes the errors in the data, the arrival times, are big enough to introduce a lot of errors in the slope. Okay, this is a typical effect of amplification of errors due to the derivative, to the differentiation operator. So sometimes you have to regularize, including a priori information. But by and large, this is a classical approach. Okay, you have 30 meters, then you have all the interval velocities, and you compute your BS30, and you're happy. Well, you're happy locally. If you have like a different formation 10 meters away, you will not realize. And this is a typical example. This is the velocity of the P wave. This is the velocity of the shear wave. And you might notice that up to a certain depth, these two are very close to the factor of 2. And then below that level, the P wave becomes much faster than the shear wave. This is because at 12 meters, you have a water table. So be aware that the relationship between velocity of P wave and shear wave, P wave and S waves, is not the one from theory of a purely elastic medium, because the medium is actually porous and it contains water. And this slide alone explains why I cannot use P wave to identify shear wave velocity, because usually below the water table, I only have some information about the presence of the fluid, saturated fluid, and the compaction, of course, of the sediments, but the relationship with the shear wave velocity becomes extremely weak, if not absent. Okay. Okay, so we have some problems with downholes, and since downholes are used a lot, let me focus a little bit on the downholes. In particular, you may have problems with coupling and in the identification of the first arrivals because of Stoneleigh waves. What are Stoneleigh waves? Well, okay, let's talk about the coupling first. Essentially, you have to make sure that the casing on which the geophone is actually coupled, is clamped, is in good contact, solid contact with the drill hole. So this annulus must be backfilled. And this is easier said than done. So you might have problems in cementing. If you have problems in cementing, this is what you obtain. So the first energy that hits the geophone will make the casing really sound like a pipe, like an organ pipe. And this is a problem because it might be the P wave, even though it is weak, it is able to make everything resonate, and therefore you will not be able to identify the shear waves. Here you have some other examples of the same kind. So you have to be careful in the way the boreholes are made. Otherwise, the borehole is useless, essentially. You may also have a problem with the air blast, because, of course, the sound, particularly if you have an open hole with no water, you may have these arrivals of 330 meters per second that are going down the hole and coming back. Okay, if you have this is filled with air only, it's not so much of may not be so much of a problem, but you have to be careful in identifying. Okay, the velocity, these are velocities. It's telling you this is a air wave. And if you have a borehole that is filled with water, on the other hand, you may not have the air wave, but you have the Stoneleigh wave. What are the Stoneleigh waves? Well, essentially, let me go back to this one. Essentially, these are waves that propagate along the borehole as an effect of the interaction between the material in the hole and the solid material around in the casing. So it is essentially a surface wave. And like all surface waves, it's powerful, it stays one-dimensional, so it does not have any geometric spreading. And it tends to have a velocity that depends, of course, on the properties of the fluid, of the solid material, and so on. And it might superimpose itself on the shear waves. It depends, everything depends on the balance between velocity of P waves, velocity of shear waves, velocity of P waves in the fluid. And this is the typical thing you observe in boreholes. Of course, you might have, here you see the Stoney wave going down and bouncing back up while the P wave is arriving first. Okay, so this may be a problem in borehole acquisition. Of course, you may also do without boreholes, the time thing. The seismic cone is a penetrometric test, essentially, where you push the pipes down, and the cone, which is a typical geotechnical instrument, is actually also equipped with a geophone. You don't drill any hole, you just push it down. Okay, this avoids essentially Stoney waves, but of course you must be able to push the cone all the way down to 30 meters, and this is only possible in weak sediments. Essentially, you will not be able to do it in high-class ground types because everything is too rigid and will not be able to run this kind of test. To conclude the borehole applications, let me just call into play something that is actually very common also in the oil industry, and not only the use of geophysical logs in the hole. Essentially, you may have a source and a receiver both in the same borehole, and you emit and you receive. Of course, you can compute the velocity. Now, there are some issues there, of course, particularly for S waves. This is a typical setup, right? You have at least one transmitter, generally it's two receivers. You lower this stuff down, and generally the borehole in this case is intended to be filled with water. Okay, this technology has been devised for deep boreholes. Okay, so essentially you emit P waves and you record P waves. So why are we interested in this kind of devices? Well, because it is explained here, maybe, but it may be a little bit easier if I gesticulate a little bit with a mouse. When you emit a P wave that is hitting the interface here, again, you generate an S wave and a P wave. So you will get essentially a critically refracted P wave that will come back, a critically refracted S wave that will come back to the receivers. Of course, coming back, it will also be transformed back into a P wave in the fluid. Okay, so everything is P, the fluid, but it is caused by an S wave in the formation. So if you look at the different arrival times in the horizontal direction with respect to the vertical direction, you may be able to identify this is the delta. Yes, this is due to the propagation of shear waves in the formation. You may be lucky and everything works, but sometimes it does not work because, for instance, if the formation, if the shear wave velocity in the formation is larger than the P wave velocity in the fluid, your refraction is actually, because of Snell's law, is going like this, it's not going in this direction. You will not have a critical angle, and therefore you will not see any P wave coming back. This means that if you are in a very fast formation, sorry, in a very slow formation, and the speed of the S wave is lower than the P wave velocity in the fluid, then you have a problem. This is just an example. I don't want to get into the detail here. Here you identify the P wave velocity and the P wave velocity, especially by doing this kind of calculations. Okay, so boreholes have some advantages, they also have some disadvantages. From the surface, and I will try to go quick because I want to get to the surface waves. You might be aware that there are two types of classical techniques when you acquire seismic data from the surface. The first is called surface or seismic refraction technique. It is based on the critical refraction of energy hitting, passing essentially from a low velocity layer to a higher velocity layer. Okay, if that is the case, then you will get the energy back, and you will be able to interpret just the first arrivals in order to get a profile of seismic velocity as a function of that. In this case, we have a problem with the need to use SH waves. And here you see the geometry that is used. Okay, so the line is this one. You hit this, be anything like something heavy on the ground. You hit it on one side, then you're going to hit it on the other side. And the receivers are also placed horizontally in the same direction, perpendicular to the direction of wave propagation. Okay, and this is your first arrivals, and you can identify the direct wave and the refracted wave. If everything works fine, everything is easy. Okay, essentially it is like for I will go faster now. It's like for classical seismic refraction, you have to hit from both sides, and the classical approach nowadays is to use tomographic reconstruction, and you may have a nice dimensional profile of seismic wave velocity as a function, shear wave velocity in this case, as a function of depth. And here you have another example. What is the problem? Well, the problem lies essentially in two aspects. One is that in order to see deep, you have to have very large offsets, because then the refracted wave coming from the deepest part will come first at those offsets. This requires, in turn, is a large source. And hitting a system like this does not allow you to put a lot of energy in the subsurface. It's like a golf player. Okay, and of course it depends on the friction that is applied. So therefore, you might have a track mounted on this beam and so on, but still you have a problem with penetration. Nowadays, there is a tendency towards using vibrating sources of a torsional type that will allow you to go further, because then you have much more energy than the sledgehammer. Essentially, the same applies for seismic reflection. Seismic reflection is easier to understand, of course. Remember that in this case, you are interested in the velocity only. The velocity is actually affecting the curvature of the hyperbola. Okay, this is a classical reflection seismic. This curvature is, in a simplest model, is called the normal move-out correction, and therefore, in order to match this, you have to identify the velocity, the average velocity to a certain depth. This is interesting as a high-resolution exploration technique for a number of reasons. It is much less used for this kind of VS estimations, because the way you estimate velocity is weak. I mean, the geometry is not, if you look at the geometry of acquisition, this is in the picture, it's a relatively large offset, but you cannot go this large as an offset, because otherwise you fail some of the hypotheses you make here. So you actually have to go relatively small distance between source and receiver. This means you have an angle of view which is relatively narrow. The velocity estimations can be wrong by 20% very easily, which may not be acceptable for the purpose, in this case, for our purpose here. So what are we left with? Well, there are some other techniques, okay, which are standard penetration tests, which have some degree of correlation. I will leave this to you just to appreciate. For instance, this is the VS from standard penetration test, and this is the actual VS from Crosswell. The difference may be substantial. Okay. Or you can use comb penetrometer tests if you manage to put everything down to a certain depth. Or you can use laboratory tests. Laboratory tests, I will only show you one that is actually interesting, which is a resonant column. But remember that all these laboratory tests have one major problem. The sample must be representative, and nobody will ever be able to tell you if it is representative or not, okay? Because you just have that sample. You assume it is representative. So the resonant column approach is I apply a torsion at the top, and I let the system react, okay? And when the reaction is bigger, you have a resonance to torsion. And that resonance depends on the geometry and the shear wave velocity. So you can calculate the velocity of the sample. You can also calculate the attenuation, the energy that you have lost, and so on. So it is actually used, the resonance column, more for situations where the system is not linear elastic. You start from linear elastic, then you get into plastic, and then you go with the kind of hysteretic cycle where you can compute the shear modulus, but also the loss of energy, the damping, because these two quantities are actually moving with the deformation, with the increasing deformation. So the shear modulus is going down, increasing deformation, and the attenuation is going up. Okay, these kind of curves are necessary if you want to do an accurate response, soil response analysis, but it is beyond the classical characterization. And then you can use other types of laboratory measurements, for instance, Bender elements, where you see this element here is a piezoelectric element that is actually shaking like this, so producing shear waves. And then you have to make sure that you don't mistake the P waves that are reflected from the sides with shear waves. So, and one of the problems with all this kind of laboratory experiments is that you have to go to high frequency, and the response to high frequency is not necessarily the same as for frequencies of interest, like a few hertz. This is the one that is the range that we are interested in. But to conclude, I will probably take 10 minutes to describe Rayleigh waves. And Rayleigh waves are used more and more because they are easy to measure and relatively easy to interpret, and you get directly information in terms of shear wave properties. We will distinguish active and passive methods. Active methods are the ones where you actually have a source that you control. This is a typical acquisition. If you hit the surface of the ground, you end up having 67% of the, theoretically, 67% of the energy in Rayleigh waves. So you don't have a problem with signal to noise ratio. These are the P waves that you use for refraction. The Rayleigh waves are much more powerful. The velocity of Rayleigh waves is about 90% of the velocity of the shear waves. So even by drawing a line here, I will be able to tell you roughly what kind of soil we're dealing with. But you can do better than that. Okay? You remember that the graph showing the amplitude as a function of depth of Rayleigh waves is of this kind, and it is normalized on the wavelength. So high frequency tend to stay shallower, and low frequency tend to go deeper. This in turn means that if the system is stratified, the low frequency will sense the deeper layers that tend to be much stiffer because of compaction. Therefore, different frequencies travel at different velocities, and you have a phenomenon that is called dispersion. Okay, dispersion means velocity variation with frequency. So the idea is I want to get the dispersion curve, because from that I can get the profile of shear wave velocity, essentially. Because, yeah, everything depends on everything, but it is a shear wave velocity that is controlling the behavior of Rayleigh waves. So let me go a little bit faster. So the idea is that I'm going to run the measurement. From the measurement, I'm going to get a dispersion curve. Then I will have a forward model, like in all the physical methods. I will simulate a dispersion curve. Once I match them, I'm going to be happy, and this will be my model of the surface. Of course, I should get down to 30 meters. Otherwise, the VS30 is not going to be computed. Okay? So measurement. This kind of approach has been first devised by, well, this is actually, it's first devised by the geotechnical engineers under the names of the spectral analysis of surface waves, where they will actually change manually the source frequency in order to retrieve the part of the dispersion curve. Hi, Gwenola. Nowadays, it is common to have multiple receivers, like the ones that you use for seismic refraction, and just use an input source. Okay? Of course, you have to have adequate geophones, low-frequency geophones. There is quite a bit of details here, but I prefer to leave the details there for further reading. Okay, but you have to use low-frequency geophones, generally 4.5 hertz, because otherwise you cut the frequencies that are more interesting for the deep characterization. And essentially, what you do is You have your seismogram, you do an FK transform. I'm sure you all know what it is, okay? And you see the energy is actually concentrating in some areas. And if you connect any point with high energy with the origin, you get a slope that is proportional to velocity. Therefore, this is already the dispersion curve. And you can do it frequency by frequency, identify the peak, and blah blah blah, and then you get your velocity dispersion curve. So you condensate everything into that, from here to there. Then you simulate your dispersion curves. There are some, of course, everything is based on the theory of elasticity. It is a matrix theory, essentially, where each layer is like a finite element by itself, okay? And the secular equation that results is just the determinant of the matrix equal to 0, otherwise you don't get any solution. And therefore, this is a implicit relationship of frequency and wave number, which essentially is the dispersion curve, the theoretical dispersion curve, given a certain sequence. So everything is in place for simple one-dimensional inversions. You may have a lot of other problems. One of the problems is that, like for a string that is between two fixed points, also the soil has multiple modes. So you may end up having a first principal mode, a first upper mode, second upper mode, and so on, in theory, because these are the solutions of the secular equation. But the energy will tend to stay in the lower modes if you hit from the surface, unless you have some strange geometries. For instance, if you have an inversion in velocity, like here, the energy, you see, jumps on the upper layers, okay? On the upper modes. And also, if you have a very strong contrast in velocity, you might have the so-called oscillation problem. So the energy jumps on the upper mode. Apparently jumps on the upper mode. Nothing is really simple, okay? And then there are inversion processes, different parameterization. Weak points of the method. Well, one weak point needs to be introduced here, because when you go to lower frequencies and you use small sources, the lower frequencies will not be present in the signal, or will be also mixed with ambient noise. And this is a typical situation. So below a few, maybe 10 hertz, the classical sledgehammer acquisition will not give you much information, which means that at depth, you don't have the information to fit your curve. And this calls into play passive methods. So let me go to that. Why are passive methods interesting? Well, essentially because they look at the background noise at every site, which is made of generally low intensity vibrations, but they contain also low frequencies. And there are two approaches to that, to this. You can use multiple sensors, maybe spread on the surface in some forms, in order to identify velocities, or you use a single sensor, and of course, a component that is solely used to identify the resonant period, or the resonant frequency of the soil, okay? Because you compare, why? Because you compare the essentially the vertical component with the horizontal components, and the horizontal components are linked to the shear waves, even though the theory is actually more linked to Rayleigh waves. But essentially, if you see an amplification in the horizontal component with respect to the vertical component, that is due to resonance. And so from this kind of measurements, you get the resonant peak of the soil, and you better be sure that it is away from the resonant peaks of the structures, okay? So these are two different uses, okay? One is to look at the dispersion curve, the other one is to look at the resonance. What can I do? Well, I finished my time essentially, but if you look at the multiple sensors, you can use a single array, or you can use multiple arrays, and in this way you identify the direction of propagation. Okay? This is a typical approach that is also used in seismology. Okay, so you see the direction from which energy comes, because you have sensors spread on the surface. A classical method is called the REMI, reflection microtremors, which actually uses only linear array, which is okay as long as energy comes from all directions, because in this situation, the minimum apparent velocity corresponds to the energy that comes in line. But if you have differential directions for the noise, for instance, this one, the lowest velocity will be higher than the true velocity of the system. And again, here you identify this is a functional period. There's nothing else but a dispersion curve. So as you see, there is a lot of, I don't have any conclusion here, okay? This is just a comparison between passive, active, and passive it is an FK spectrum essentially. And you see that you get, if both are okay, you get comparable information. If you mix the two, you get the best out of two worlds.